Right, so then welcome again to the plane algebraic curves class today. So we were discussing, we had introduced so far affine plane algebraic curves. Just to recall, this was just defined to be a polynomial over a field in two variables, modulo units, multiplication by units. So a curve here always means a plane algebraic affine curve for the moment. So I'll just only say curve is a polynomial, and we said like it should be a non-constant one to exclude like empty sets or something like that. So non-constant polynomials in two variables over any ground field, which at the moment we don't want to restrict. And then we take this modulo units, where the units are just k without zero, right? K star, so just the constant. So multiplication with the constant doesn't change that. And the last things we've shown last week are, so just two things to recall. Namely, we said something about how many points that curve contains, in the sense that this polynomial is f. We defined the set of points, which we called v of f, and that's what one maybe usually might want to call a curve. That's just the set of all points in the affine plane, which we write as a2 or a2k, such that the polynomial f at this point is 0. And we showed something about like this being infinite and the complement being infinite for certain fields. Namely, we've seen that if k is algebraically closed, then this set of points v of f is always infinite. And we showed that if k is infinite, which is a weaker condition, then the complement, so a2 without v of f, is infinite. And what we want to start with today is looking at the intersection of two curves and show that this is actually finite, as long as they don't have a common component. Right? So, of course, if you take the same curve twice, the intersection will not be finite, but otherwise it is. And so the proposition here, it's a little different to what's currently in the notes, but I'll change this. And the proof is pretty much the same. There's just one additional statement to that we want to add. Namely, the statement would be, let's take two curves. So let f and g be two curves in the sense up there. And I want to assume that they have no common component. Which, if you think of them as polynomials, means that they are co-prime. So they don't, like if you list the irreducible components, they don't have any in common. So, i.e. the polynomials are co-prime. And we assume that we have an algebraically closed field. So curves without common component over an algebraically closed field. Well, we don't need that, right? So not for that one. It's just saying finite. No, that's always true. Keep it in the second. So we just have two curves without common components. And then there's two statements. And the first one, an auxiliary statement, but we'll need this later on, is that then the ideal of f and g of these polynomials inside the polynomial ring does contain a non-zero polynomial that depends only on x. Right? So f and g are polynomials in x and y. But you can form a combination so that it depends only on x. So this contains a non-zero polynomial that depends only on x. And of course, by symmetry, you can do the same for y. So that's the first auxiliary statement, and what then very quickly follows from that is that the intersection, so the common zero locus v of fg, So it's like the notation from that time is actually finite. So essentially that tells you if you have two curves without common components, then the intersection will be finite. And we'll study this finite intersection then very much in detail in the next chapter. But first of all, we'll note that it's finite. So for the proof, part A is somehow the main part. Find such a polynomial. And so we've assumed that f and g are coprime as polynomials in x and y. So in this ring, right? So by assumption, f and g are coprime in the polynomial ring. And I claim that they are then also coprime. In the larger ring, where you take the rational functions in x. So recall that we had this ordinary, like curly brackets, round brackets notation saying that these were rational functions in x. And then adjoint y. So that means this here would be the space of all fractions, where you have and can have an arbitrary polynomial in x and y in the numerator and a polynomial, a non-zero polynomial, depending only on x in the denominator. So that would be the thing here. So the elements in here like f over g, little f over little g, where the denominator depends only on x and f can depend on anything. So that's a larger ring. I claim that they are coprime there as well. And so why is that? So assume not. Just the claim, so it's like a proof of the trait. So if not, then we could factor out like common factor from f and g. So we could write like f is some, say, h times f prime, and g is some h times g prime. So f prime and g prime just being any other elements, polynomials. So it's not the derivative, it's just any other polynomial. And where these things could have denominators, right, in x. And I want to actually clear these denominators right away. So if there's any denominators depending on x here on the right-hand side, I'll multiply with them and put them on the left side. And like if there's two of them, two different ones, I can just take the least common multiple. So I can, in any case, by multiplying with the denominators, I could put another, which I call a in here, which depends only on x, and then these would all be polynomials. So this would be after clearing denominators. So where so a depends only on x, and clearly it's non-zero. And f prime, g prime, and h are polynomials. So they could be anything in kxy. And if they are coprime in this thing, that means the degree is only measured in terms of y. And so if there's a non-trivial common factor, this means that this non-trivial common factor h is at least linear, right? So the degree of h in this variable y is at least 1. So that means like the y degree of h is at least 1. So that means it's a common factor in both of them if you consider it as a variable, as a polynomial in y. Right, so that would mean like there's a common factor, but I write it again as polynomials by multiplying with this a. So it's nicer to deal with polynomials. That is because like as this is a polynomial in x now, like each irreducible factor, so this here is now an equation in kxy, these are equations in kxy, we have a unique factorization domain, and that means that every factor, every irreducible factor in A must be in H or in F prime. And actually, as we have the same A on both sides, it's either in H or in F prime and G prime simultaneously. And I'll just take all those factors and then divide it out of H or of F prime and G prime to clear this A as well, so that we don't have any X more. And if dividing by those polynomials in x will not reduce the y degree, of course, in h, so that would still be true. So we could now, so for each So each, like this, each irreducible factor of A is then contained in H, or F prime and G prime. And that means we could factor this out. So divide by it, which does not change the y degree. And that means after relabeling this H, F prime, and G prime, I can essentially assume that this A is 1. So that means all of these factors I put in here and divide this by those factors that are in here and divide this. So that means I'll get a new representation of the form F is H, F prime, G is H, G prime, with the y degree of H still being at least 1, and these are now all polynomials, and that's of course a contradiction to that F and G are co-prime, because these are now polynomials, and that equation tells you that it would also not be co-prime as polynomials. So this is a contradiction to F and G co-prime in the polynomial ring. So that's just like a initial observation that when they are co-prime in the polynomial ring, they are also in this larger ring. So why I'm doing that? So the reason is that this is now a polynomial ring in one variable over a field, like K round X is a field, and a polynomial ring over a field in one variable is a principal ideal domain. Right? So we know that from the algebraic structures class, and in such a principal ideal domain, we can represent the greatest common divisor as a linear as a combination of the other two. Now, AXY is a principal ideal domain, or Euclidean ring if you want to. Also true and insufficient here. So as it's a polynomial ring in one variable over a field. And that means that the greatest common divisor of two elements is a combination of the elements, linear combination of the elements. So that I'm assuming here from our algebraic structures class where we do that. And that means as these are co-prime now, F and G in this ring, that means I can write 1 as a linear combination of the two. So that means I can write 1, which is the GCD, which is common divisor of F and G, is, well, some multiple, say D times F plus E times G. And that again would hold now only in this ring with fractions, like where you can have denominators of x where you can have a polynomial in x in the denominator. So again, I want to clear these denominators, and if like D and E have anything in the denominator, I just multiply with them to put it here. So again, after clearing denominators, I don't have a 1 here, but anything I think I call it C in the proof. So that again would hold then after clearing denominators. Where now C is a polynomial only in X, which is non-zero, and D and E are just polynomials. And that's it, right? So that means now I have a polynomial in X, which is C, and it lies in the ideal generated by F and G in the polynomial ring. And that's exactly the statement A. So we have a non-zero polynomial, which is here C, which we can write in that form, hence it's in the ideal. And that's the statement A. Why this helps for B is just simply now if we have in the common zero locus of f and g. Now, if f and g are 0 at a point, then c is also 0 at a point. So that equation. But that's a polynomial now in one variable x. And if that is 0 at the point, that restricts x to one of these finitely many zeros. And a polynomial in one variable has finitely many zeros. So that means this equation tells you that the x-coordinate of any common point in f and g must be a 0 of c, and there's only finitely many. And the same you do with y, and then you have only finitely many choices for the x and y coordinate, and hence there's only finitely many points. So that is b, like continuing that from a. We say now if p is in the 0 locus of f and g, so in the 0 set, then the f of p and g of p is 0, which means that c of p is also 0. And that means it restricts the x-coordinate of p to be one of the finitely many zeros of c. Right, and the same is for y. And so there's finitely many choices for both coordinates. So there's only finitely many points. So hence you get what one would probably expect, like from two curves, two one-dimensional things in the plane, that they intersect in finitely many points. Unless they have a common component. But yeah, it's the same for y. And we get only finitely many points in the intersection. And we have fg. And that's the second part of the proof. So depending on what your background is in commutative algebra, I mean, you maybe have other proofs of that. I mean, using if you know commutative algebra and dimension theory, and so like, I mean, you'd say like this is a 0-dimensional thing because for whatever reason you have from commutative algebra class. But these are just elementary methods. They would also show. Right. Any questions here? If not, then so what's the corollary? I mean, where did we come from, actually? We wanted to know, I mean, besides that this is a nice thing to know, actually, and that one as well, is that we wanted to know to what extent the 0 locus v of f actually determines back f. Because most of the time, I mean, people would probably say a curve is a 0 locus in A2. And we somehow deliberately chose not to say this, but say it's a polynomial. So in what sense does it go back? And the statement here is, and there we now need that K is algebraically closed, so that f be a curve over an algebraically closed field. Algebraically closed field. And then the statement is then for any irreducible curve, B, we have that G divides F, so that means G is a component of F if and only if V of G is contained in V of F. And that in particular means that all the irreducible factors can be read off from the V of F, from the V's, right? So if I only know V of F, then I could determine whether any polynomial is a factor of that or not from V of F. So in particular, V of F determines all components of F. However, not their multiplicities, right? So we can say whether an irreducible factor is contained in F, but we cannot say with which multiplicity. And we've already seen that. I mean, last time the example is quite obvious. I mean, if I just put any exponent to an irreducible factor, so f and f squared have the same zero locus. So there's no way to distinguish what the multiplicities are if I only know the zero locus. So it determines all components of f, but not their multiplicities, of course. But at least the components, and that's quite good because it means that if we draw a picture of v of f, that's already quite a lot of information. So we know all the factors contained. So the proof of that is now quite simple. I mean, one direction is really simple, right? If g divides f, so this means f is g times something, then if g is 0, then f is 0. Right? That's, I guess, the one direction. So say let g divide f, i.e. f is g times h for some h. Then, of course, if we have p and v of g, that means that g of p is 0. But that means that f of p is also 0 because f of p is g of p times h of p. And that's also 0. So that means p is also in v of f. So that direction is clear. So there we don't need any of the results up there. The other direction, but also, I mean, that's sort of clear because it seems to us that the polynomial itself is more information than the zero locus, right? So if we start with something about the polynomials, that we can deduce something about the zero locus should be not too surprising. So the maybe surprising thing, and also where we need the algebraically closed condition, is the other direction back. But which now with the proposition up there is also quite simple. Namely, now we assume that v of g is contained in v of f. That's the direction backwards. Now assume v of g is contained in v of f. So that means whenever g is 0, f is 0 as well. In particular, that means that v of g, v of f and g is the same as v of g. Right? That's what this says. So if g is 0, then f is 0 as well. So that's the same as that. And if I put f in there, it doesn't make any difference. But now we've seen that this thing here, v of g, v of one polynomial up there is infinite. And that's the first line up there. If k is algebraically closed. So this is infinite by last time. Okay? But it's also v of fg, and if v of fg is infinite, then our proposition just tell, well, then they cannot be coprime. Okay? So that's the proposition up there, saying that then f and g are not coprime. Otherwise, the intersection would have to be finite. But if they are not coprime and g is irreducible, then the only way this can happen is that g divides f. And that's the other direction, right? So that means that's quite a simple consequence of the intersection of two of the curves being finite if curves are coprime. Well, and that, as I said, it means that the geometric picture, so the picture in A2, just determines pretty much f except for the multiplicities. And that means we can get a complete picture of f. So if we really want to determine back f, we just have to attach the multiplicity to every component. So another way of saying this, or in other words, f can be determined uniquely by drawing v of f and attaching a multiplicity to every component. Every component. So, for example, if we have f, whatever, maybe we have a look at the real, well, I mean, R is not algebraically closed, but of course I cannot draw complex pictures. So let's cheat a bit and draw real pictures. So if you have something like the unit circle and if you multiply it maybe with x plus y to the 3 or something, that will be a polynomial with its unique factorization. Then if I draw a picture that has the one component here with the multiplicity 1, so I could just write it as a number there, put it here, and the other one, the 0 locus, would be that, and this we have with a multiplicity of 3, then this would be like a complete picture determine this polynomial over an algebraically closed field. And so that is, of course, the general idea of algebraic geometry, that you want to have a dictionary between algebra and geometry. So on the algebra side, we're working with polynomials, and now we have an entirely geometric picture that you can draw on the board, and that determines the same thing, right? Polynomial. And actually having these multiplicities is very nice. So when we deal with these curves for many purposes, it's actually good not to forget them. And that's why we defined curves. So in principle, that tells you that if we define curves as subsets of A2, we would get pretty much the same thing. We just forget the multiplicities. And we'll see in many applications that we don't want to forget them. So that's why we have this different definition. But as that really relates very closely like f to its 0 locus, I mean, we will also abuse notation a bit. So the notation, so as f and v of f, say contain in the sense almost the same information, except for everything except for the multiplicity. We'll also use some notations for f, although it's a polynomial, although it's a curve, as if it was a set. Namely as follows. So we'll say abuse notation and write so a couple of things. For example, we would write something like P is in F intersect G. So if you think of F and G as curved, I mean, you would clearly know what is meant. So what I mean by that here is just P is in V of F comma G. So for P is in V of F comma G, which would be the same as V of F intersect V of G. So essentially we drop the V in that notation, because that should be unambiguous, I think. And you would write just F intersect G. So if F and G are curves, the intersection is meant to be V of F comma G. We would write the union F union G. We write this for the product polynomial because that's one whose 0 locus is exactly that. And finally, we would write, so there was one more thing here, yeah, like the containment, right? So if we would write G is contained in F, so one curve sits inside another, or G divides F. So that's somehow the geometric notation, I would say. So if you think of F and G being curves, not polynomials, but subset of the plane, then it's somehow clear what you mean by that, and that's what's actually meant by definition. Right, and then we are pretty much back at how you would usually write down things for curves. Yeah, so that's the first chapter actually on affine curves and very, very first properties. So any questions on that? So now we want to start to discuss, of course, properties of these curves. And one thing that we've seen already now is that the intersection of two co-prime curves, at least without common component, is finite. And that, of course, leads very naturally to the question, well, how many points does it contain, the intersection? And which would be a generalization, sort of the question, how many zeros does a polynomial have in one variable? And so here we have two polynomials, and the corresponding like not plane curves, but polynomial on the line question would be how many zeros does a polynomial have? And then you would want to say, well, a polynomial of degree n has n zeros. But of course, you know that this only holds under special circumstances, even if k is algebraically closed. Then you somehow have to count the points with multiplicities, right? There's something like double zeros, multiple zeros. And that concept we have to introduce here. And that's the second chapter, which is about intersection multiplicities. That's the name for that. So the motivation for that is the following. So it generalizes the concept of multiplicity of a zero that you know from a polynomial in one variable. So if we have a polynomial, let's write it like little f. We don't want to think of it as a curve at the moment. A polynomial in one variable is, say, a polynomial in one variable. Then we can, and we have a zero of that, say any point a and k, such that f of a is 0, then we know that we can factor out x minus a certain number of times. So we can write f is x minus a to the m times some polynomial g, where g does not vanish at a. So g of a is not equal to 0, and then you would call m the multiplicity of the 0a. M is the multiplicity of the 0a in F. And that is, of course, a geometric thing. So if we draw pictures like of polynomials, here's x, it's f of x, then we know like if a is here, like a simple 0 would usually look like that. So a curve that just goes straight through. Whereas if we have, for example, a multiplicity of 2, then it looks like a tangency, like this, to this x-axis. So this is x, and this is f of x. So that in this notation would be m equals 1, and this would be m equals 2. And similarly for higher numbers of m, of course, right? So if m is 3, then we have something like, well, something that looks like x cubed, right? So something that even better approximates the x-axis here at the point. Here we have a, what one usually calls like a transverse intersection of those two, of the curves and the x-axis. And here we have a tangency. And for higher m, we have sort of a higher order tangency. We want to generalize that to arbitrary curves. So here we have now like the two orange things. So one of them is always the x-axis. But if we had two curves and intersect them, then there would also be pictures similar to that, right? You can think of one branch of the thing as one curve and the other is the other curve, and you want to study how they intersect, like whether they intersect transversely or whether there's a tangency in the intersection. And that's what we want to do now. So somehow generalize that picture so that we can not only take a polynomial in one variable and intersect its graph with the x-axis, but also can intersect two curves and study the same thing, right? So we want to generalize this to arbitrary curves f and g, still meaning plane curves, of course. So we want to generalize to plane curves f and g. So that means this picture would then probably look like similar like that. So this would be f. This would be g, strictly speaking, v of f and v of g, like it's the geometric picture. And if it looks like that, sort of, we would want to call it they intersect with multiplicity 1. We would say the intersection multiplicity is 1. Whereas if it looks like that, so if like this was f and this is g, then in this point here, also in that point, we would say that the intersection multiplicity is 2. And similarly for higher numbers, of course. And so there's something like that we want to define. And in fact, we'll see later on in class that when you count the number of intersection points in the same way as when you count zeros of the polynomials to get the total degree, you would also do well to count these intersection points with their multiplicities, and then you would get a nice number at the end. So that's one reason why to introduce that. Besides that, we can use them, of course, to distinguish algebraically whether there's a tangency or not, or even to define what tangency means. And because that will be a concept, so we'll define this number now, this intersection multiplicity, and see that it's like an entirely algebraic object. Well, it has an algebraic definition. We can compute it quite easily, and that's what we want to do now. So the question is now how to define that. Well, first, write down the definition, and then we'll collect a couple of properties that will then gradually show that this is the right concept. So depending on how much you dealt with, say, commutative algebra already, or with these geometric objects, it's more or less obvious that this definition does the right thing. So probably it's less obvious, but as I say, we'll see many properties that will reassure us that it's the right thing to do. So the question now is how to define this. And so for that, we need a construction first, and then we need local rings. And so local rings, if you had been in a commutative algebra class, you would know what that means. Like there's an algebraic definition of local, but there's also a geometric version of local in the sense it's something around a point, and that actually coincides. So one name comes from the other, and so you might think of this in the geometric sense if you want to. Namely, there is something that we would call local rings of the affine plane. And that works as follows. So let's say we pick a point in the plane. So let P and A2. And we define the local ring of the plane at P. That's its name. And we'll see that it's both a local ring in the algebraic sense and in the geometric sense. So we define the local ring of the plane at P as, so the standard notation for that is a curly O. You can distinguish it from a zero, so it's a curly O. And then you write A2, comma P, so of the space at the point. But as at the moment, I mean, there will be no other point, so I'll often just, there's nothing else in the plane, so I'll often just call it OP. And what this is these, so let's first write it down in that sense. It lives in the quotient field of the polynomial ring. Its quotients f over g, where f and g are polynomials in two variables. And the denominator doesn't vanish at p. So g at p is not equal to 0, and that sits inside the quotient field. So a in round brackets xy, which was the quotient field of the polynomial ring. Right? So the quotient field here was just anything like that where g is non-zero. And now we take only those ones where g is non-vanishing at the point P. So that's called the local ring of A2 at P. I mean, obviously it's a ring. I mean, you can multiply those things and add them. That works. And well, we can remark then afterwards that it's also in the algebraic sense a local ring. So the second thing B is, well, if you know already from commutative algebra in that case, you know a local ring should have a unique maximal ideal. I mean, that's the definition. And in fact, this one does have a nice ideal, maximal ideal sitting inside it, namely all those functions where the numerator vanishes, actually. And the point is that if you have these fractions f over g, where g is not equal to 0 at p, that means that you can plug in the point p at this thing to get a value. So there's an evaluation map, which is actually a ring homomorphism. Ring homomorphism. At P, namely that goes from OP to K and takes such a thing, so F over G, and maps it to F of P over G of P. Right, so that's well defined because G of P is not 0, and it's a ring homomorphism. And that one, well, has the kernel, which is an ideal, And that would be the ones obviously where P is 0. So its kernel is, so I want to call this I, as it's an ideal, P2 at P, A2 at P, or I just write it as IP. And that would be the same thing as here, just that F is 0 in addition. And so it means we take F over G, that F and G is in KXY, and still G of P is non-zero, but F of P is equal to 0. Right, and that's an ideal, obviously. I think like ideal of all P. Yes, so maybe some remarks about this construction. So both regarding geometry and algebra. So why is this local in the geometric sense? So what this ring describes here is, so I think I said already, like in algebraic geometry, the nice functions, so whatever in analysis would be differentiable functions or maybe in topology continuous functions, are the functions that are quotients of polynomials, because that's the only thing you can do algebraically. You only have like plus, minus, times, and division, and that's the thing that you can form. And so that means these would be the nice functions, like in the algebraic geometric sense, that you can evaluate at the point P. I mean, to be able to evaluate it, the denominator obviously has to be non-zero. So these are the functions that are exactly the functions that are defined at P. And as they are, well, continuous in a sense, right? In the usual sense, if you want to, like over the real or complex numbers, that means they would also be non-zero in a neighborhood, and so they describe functions that are well defined locally around P. And then that's where you could, how you could imagine why you call this a local ring in the geometric sense. So in the geometric sense, this ring, so OP describes functions that are well defined in a neighborhood of P. Right, and that's why we call it geometrically a local ring. That's where the name comes from, if you haven't seen it in commutative algebra. If you have seen it in commutative algebra, then you know, of course, like a local ring is one with exactly one maximal ideal, and that is actually it, this IP. In fact, pretty much by construction, then this ring would be the localization of the polynomial ring at this ideal. Right? So in case you've seen that. So if not, then it doesn't matter. So in the algebraic sense, this is a local ring. So IE has a unique maximal ideal. Which is just this IP. Well, since, for example, it is pretty much by definition the localization of OP at IP. And so if this doesn't make sense to you, just ignore it. But I think, I mean, a couple of you had already a commutative algebra class. Right? So that means it's both local in the geometric and algebraic sense. In any case, what we will need, and what's kind of clear even without that, is we had said that like the polynomial ring itself, so kxy in square brackets, is of course an integral domain with units just the constants, and it was a unique factorization domain, and that carries over quite obviously to this quotient field and hence also to OP. So that means that would be still an integral domain, and the units actually do change, because we now have more things that we can divide by. Then all the polynomials that are non-zero at P will become units. So that means we have more units than before. Properties. So it's just this then, so say OP is an integral domain. It is, let's say, just as the polynomial ring, it just inherits it from that. So as kxy, it is factorial. There's a unique factorization with the irreducible elements. They would now be all irreducible polynomials, but those only that are 0 at p. Because all the others would vanish, right? Because any polynomial that's not 0 at p will become invertible and it's a unit. So you just drop those. So the irreducible element, the irreducible polynomials vanishing at p. And make the other ones become units. So that again would sort of be an interpretation of the word local, right? So in the ordinary polynomial ring, you had all the irreducible elements, are all the various curves that you have, but here you drop every curve that doesn't pass through the point. So you just forget about them. And again, that you could call as looking at the local pictures, so you only keep those ones that pass through the point. So these are like the properties of this ring. And this ring is actually now used to define this intersection multiplicity. Namely, we define it as taking this ring and forming the quotient of it modulo the ideal in it generated by the two curves or the two polynomials, and considering the rest only as a vector space over K and take its dimension. So that would be the definition. And as I said, so if it's not clear at the moment, which probably it is, why this is a sensible definition, then we will see this within the next hours or whatever. So the definitions, let's say let f and g be curves or polynomials, doesn't matter. So that we use them as polynomials, but we only need it up to units, so that's fine. And p a point in A2. Then we define the intersection multiplicity of f and g at p. Of f and g p, as he said, it will turn out to be the thing that we just motivated geometrically, so we'll denote this by mu. And then the point, p of f and g, and that be defined as, so you take this local ring, you mod out the ideal that is generated in this local ring by these two polynomials, and then take the dimension as a K vector space. It's really like a linear algebra dimension. It's not a commutative algebra dimension, right? Not cool dimension, but linear algebra as a K vector space. And so the result would be, it's just, I mean, either it's a natural number or it might be infinite, in case that's an infinite dimensional vector space, right? So we don't know anything about that at the moment. That would be the definition. As I say, so we'll see soon why it makes sense to define it that way, why this does the right thing. Yeah. So let's start with a few remarks about this. There's many remarks that you could do at the moment to start with. So the first one would be what we actually will often do, not always, but maybe often, is what should also be clear geometrically if we define a sensible thing here, is that for these pictures here, it doesn't really matter where you put them in the plane, right? So if you shift the point P to the origin, for example, and shift all the polynomials to the origin, it shouldn't change anything. And that's pretty much clear from the definition. So like remark A is, if we consider an affine coordinate transformation, so for an affine coordinate transformation, So what's meant by that is we have some x prime and y prime, and they are determined in terms of x and y by, say, some ax plus by plus the constant, and here gx plus ey plus some constant f. A, B, C, D, E, F are just elements of K, and that should be invertible. So that means probably AE minus BD is non-zero. That just means it's invertible. You can actually transform the whole thing and get the same result. So I mean, if you express both the point P in the new coordinates and the polynomials in the new coordinates and form the same thing, then you will get an isomorphic space and hence the same number. We obtain that mu E prime of F prime and G prime is the same as mu P of F and G, where P prime is the image of P and F prime and G prime are F and G expressed in these new coordinates. So F prime and G primes are F and G expressed in X prime and Y prime. And so what that means, I mean, that's pretty much clear from the definition, but that it means that we can usually assume, if we want to, that that the point is the origin, for example. We shift everything to 0, right? So it's invariant by translations. And some formulas for intersection multiplicities or some results are just simpler to state if we're at the origin. And that means we can just do that. That means we can often stick to the case where P is the origin, and this we can do without loss of generality. For that reason. There's two more obvious remarks. I mean, one is clearly, but let me just write it down, that this thing is symmetric clearly, right? So that means mu P of Fg is clearly mu P of Gf. There's a symmetry here. And the last thing is, of course, any transformation that leaves the ideal invariant would also leave the multiplicity invariant. And one important thing for that is that mu P of F and then G plus F times something times H would be the same as mu P F G for all FGH, since, of course, the ideals generated by these two things are the same. So the ideal Fg is the same as the ideal F and G plus Fh. So that's already quite a non-trivial thing you could do with the two polynomials, with the two curves, which doesn't change that. Quite a number of times used that property. So it's geometrically not too obvious probably what we do there, but algebraically it's quite clear we don't change the ideal. Yeah, that's one very first remark. And let's maybe start proving some sort of small lemma. Namely, so as I said, at the moment, we don't know pretty much anything about that number, which values it takes, when does it take which values. And the first thing maybe one wants to know is how this intersection multiplicity even captures the fact whether the curves intersect at the point. I mean, we haven't assumed here that P lies on F or on G. And so this number would be defined also if P is a point just somewhere completely else. And obviously, if this defines the correct notion of intersection multiplicity, that should only be non-zero if the point even lies in the intersection. And that's actually true, and that would be like our first lemma. So for that, we let again F and G be curves or polynomials. And P a point. And then the first statement is that the intersection multiplicity is at least 1 if and only if they actually intersect in P. That means mu P of F and G is at least 1 if and only if P lies in the intersection. So in the sloppy notation, I would write it like that. And B, there's also a condition when it's actually equal to 1, namely if and only if the ideal generated by F and G is this IP that we had up there. So the intersection multiplicity F and G is equal to 1 if and only if the ideal of F and G is the same as this ideal IP in the local ring. So that reassures, like the first thing at least reassures that at least it captures this idea whether the things intersect at the point P or not. So that is actually not too hard from the definition. Namely, let's maybe distinguish between the two cases whether P lies in the intersection or not. So say if P is not on F, so if P is not in F, which means F of P is not equal to 0. Well, what happens then? So if F of P is not equal to 0, then this F is actually a unit in the local ring. Right? So we could invert anything that's non-zero at P. And that means F is a unit. In OP. And that means, of course, that the ideal generated by F and G is just the whole ring. And that means that the quotient here is just nothing and we get 0. Right? Just by definition. So that means the ideal F and G is equal to OP, which means that the local intersection multiplicity mu P of FG is actually 0. And that shows pretty much everything, right? Because, like, well, I mean, this is then false, and this is false because P is not in F, and this is false, and this is false again because FG is OP and not IP. And so I mean, that shows already both statements in the cases that P is not on F. Well, that shows A and B in this case. So if P is not in F. And of course, similarly, we get this if P is not in G. So that shows already if P is not even in the intersection, we trivially get 0 in the definition. So let's assume it is on both one. Now, assume P is in the intersection of F and G. That means both of them vanish at the point. Right, the F of P and G of P are both 0. What that means is that our evaluation map that we had, like from OP to K, evaluating at the point P, factors through the quotient of F and G, because F and G are 0 at the point. So the evaluation map factors through or descends to a map OP modulo FG to K. So we had it only without that. We had the regular evaluation. But if F and G are 0 at the point, you can pass it here to the quotient and still get a well-defined map. So that's still a ring homomorphism. And it's clearly surjective, right? Because we have constant maps. One maps to one. Which is a linear surjective map. Okay, linear in the sense of vector spaces. A linear surjective map, and that's only possible if that dimension of that vector space is at least 1. And that dimension was by definition UP. And so UP of F and G is at least 1. That's A. And we can just upgrade this to B because, well, when is the dimension equal to 1? We still have this surjective K linear map. Of course, then the dimension here is exactly 1 if and only if that's an isomorphism. And it's an isomorphism, like we also have the isomorphism theorem, like saying that OP modulo the kernel of this map is isomorphic to the image. So that means it's an isomorphism if and only if this is actually the kernel of the evaluation map, and the kernel of the evaluation map is IP. And so that. So in addition, and that shows B. UP FG is equal to 1 if and only if this map is surjective, is an isomorphism. Which means that by the homomorphism theorem, that the idea that we mod out here, FG, has to be the kernel of the map, which is IP. Yeah. So that's like the very first property of that thing. So at least it being 0 or non-zero captures whether they intersect or not. Can maybe do a simple example. Namely, one thing that one would clearly expect is that when we intersect the two coordinate axes in a plane, that we should get 1, right? And that we can actually check. So it's a very simple example now. Namely, IP. So let's do this in the origin. So A0 in O0, so at the origin, is, as we said, it's generated, it's all F over G, where F is 0 at the point in G naught. And that F is 0 at the point means it doesn't have a constant term. So this consists of all F over G such that F of 0 is 0, i.e. it doesn't have a constant term. And the polynomials that don't have the constant terms are generated by x and y. Because any term must have an x and a y, or y. And so that means this I0 is the same as x and y. What that means, so this is satisfied if f is x and g is y, and so that means the intersection multiplicity of x and y is 1, so by part B, and x and y are just the two axes, right, in terms of polynomials. Hence, by our lemma B, we have that the intersection multiplicity at 0 of x and y curves is 1, and the picture is of course just the same. So that's the very, very simplest case of an intersection multiplicity, just two lines intersecting at a point. And you would get 1. So that's maybe the first statement. So when do we get a positive number? When we do get 1. So we have a criterion for that. Any questions? So now I want to just switch a little bit from the actual notes because it changed in the new ones. Namely, the next question, and we can actually answer this now. So in the notes, in the old notes, I made it later on, but it's nicer to have it now, and I found a way to do it. Put it on the homework actually this week. It's not that bad. Is the question whether this number is actually finite or not. Because that's not clear, right? So we've defined any vector space here, and we don't see at the moment whether it's finite or infinite dimensional. And in fact, what one might expect from geometry, I mean, what we probably do expect from geometry, if this captures the right notion of intersection multiplicity, that number should be finite, unless the two curves somehow touch to infinite order, and touching to infinite order in here in that sense means they are just the same. So if we have two curves, I mean, for irreducible curves, it would mean the same. For arbitrary ones, it would mean they have a common component at the origin or at the point that we consider. So if that happens, then we would get an infinite answer, actually. And if not, we get a finite one. And that's actually on the current homework set. Our next question would be, is mu p FG finite? And so the answer, as you see, is on the homework together. So with a sort of like, with sort of instructions how you could do that. So the result, which then simplifies a few things further on, if we know this already now and not just later, is that so if the f and g do not contain a common component through the point P, then the number will be finite. And if they do, then it's infinite. So we'll see. Homework. So these are exactly two cases. So if f and g contain a common component, or let's phrase it the other way first, which is the more interesting one, do not contain then the intersection multiplicity of f and g is finite. And vice versa it holds as well. So it's an if and only if. So if they do contain a common component, through P, that's important. If we really only care about the point P through P, then it is infinite. And I guess from the geometric interpretation, both of them should be expected. I mean, because this number should be like the order to which the curves touch at the point. Higher number means they touch more, like they agree more around the point. And infinite means they actually agree completely. They are the same curve locally around the point. And if not, then you actually get a finite result. So I said we'll see this on the current homework set. Yeah, so for further results, actually, there's one important result that we need on the intersection multiplicity, namely that it's additive in the sense that if one of the two curves, say f, is a product of two, so this is like an f1 times f2, then you can split this into two and you make it an f1g plus f2g. So it's sort of bilinear in those two entries. And to see this, we actually would need to consider a certain exact sequence. We have to talk about exact sequences. So my question would be, have you seen exact sequences before or not? So you have, you do as well or not? I mean, if not, I'll just quickly say something about this. We only need it of vector spaces, so it's just like an exact sequence. If we're not, then I say something about this. Okay, so then I say something about this. So there's one more important property of this intersection multiplicity mu p, and for that we need and actually we'll need this a couple more times in the class, so it's not only for that one, but it's a very like ubiquitous statement thing in commutative algebra, namely so it's we call it like definition or construction. What do you call it? Construction. We only need short exact sequences here. And I'll really take the quick and dirty way here because, I mean, if you've seen it somewhere else, I mean, then you know clearly in more generality than here. So here I'll take like the simplest case possible, and that's the only thing we need. Namely, of vector spaces over a ground field and short ones, so really only three terms, and it looks as follows. So we say a short exact sequence of vector spaces over a field is a sequence of linear maps. So K linear maps as vector spaces. So we have a zero vector space that's somehow conventionally in the notation here. And then you have three vector spaces, U, V, and W. And there's a linear map here, we call this phi, and there's a linear map here, we call this psi. And so that is pretty much just notation. And the map here, of course, is trivial because it's a zero vector space. There's only possible map. So it means we have to give three vector spaces and two maps. And the condition is that, and that explains a little bit the zeros, that at every point in the sequence, the image of every linear map is the kernel of the next. And that leads to three conditions in that thing. So, of linear maps such that as I said, so at each point, like here and there, the image of the map going to it is the same as the kernel going to the next. And that means in the first part here, the image is just 0. So the kernel here should be 0. So we want that the kernel of phi is 0. So here the image of phi is the kernel of psi. And here the kernel of psi is the image of that. So the image of psi is the kernel of that, and the kernel is everything. So that means the image is everything. So the image of psi is all of W. So these are the three conditions. If we have three vector spaces, two maps like this, and it satisfies that, you would call it a short exact sequence. So there's exactly one thing that we will need about this. So we'll just see such a short exact sequence in a minute. And there's exactly one thing we need to know about this, namely that the dimensions of the vector spaces then just add up in the sense that the dimension of U and W together is the dimension of V. Then we have let's see why this is the case. So let's consider the dimension of U plus the dimension of W. So that actually holds regardless of whether they are infinite or finite dimensional. So let me try to be careful not to use a minus in the proof. Then it holds also if there's infinity contained in the equation. So the dimension of U and the dimension of W, how can we rephrase them? So what? Is there something wrong? Kernel, image, everything here, right? Anything? Dimension of U, if phi is injective, then the dimension of U is the same as the dimension of the image, right? Because it's an injective map. So the image has the same dimension. I can write this as the dimension as the image of phi. The last map is surjective. So if it's surjective, then W is the image of psi. So I can write this as the image of psi. So that works. So that's U, that's W. Now I'll use the homomorphism theorem once and write instead of the dimension of the image of psi, I'll write the dimension of V modulo the kernel of psi, which is the same. They're isomorphic spaces. So that's the dim in phi. Then V modulo the kernel of psi. But the kernel of psi is the image of phi. So that's dim in phi plus dim V modulo M phi. And that's just dim V. Right? And that's pretty much the only thing we'll need about this. So if you've seen this before, you know like 100 more things about these exact sequences. If not, then this is all we need. Because what we will do now is we'll write down an exact sequence among these rings like OP modulo some ideals. And if we have this, then these dimension statements here will just be equations among our intersection multiplicities. because they are the dimensions of these spaces. And that's in our next result here. Which we call like the additivity of intersection multiplicities. That's a proposition, really. So, which we call additivity. And we'll see that with this proposition together, we really then have enough information to compute this thing in all cases. We'll see this later on, not today, but then next week. And that works as follows. So we have, again, two polynomials, f and g, and a point where we consider it. Well, let f and g be curves or polynomials. And p in A2. Actually, we need three of them. F, G, H, P curves are polynomials, and P a point in A2. Then A, under the assumption first that F and G do not have a common component through P. So if they don't have common component through P, then there is an exact sequence like that. Looks as follows. So same notation with there. We start with 0. Then we have OP modulo F and H. Then we have OP modulo F and GH. And then we have OP modulo F and G. And then 0. So these are all we consider it now only as a map of vector spaces, of K vector spaces for that thing. We see that I made them in the right order. Otherwise, nothing will work out at the end. So FG and FG. Yeah. And the maps in between here are, so this here map is multiplication with G, with the polynomial G, and this is just a natural projection, which doesn't do anything. Like the class of anything goes to the same class modulo the other thing here. So this is just a natural projection. And what follows from that, of course, then, if you write dimensions in front of it, that means the dimension in the middle is the sum of the dimension on left and right. And that are the intersection multiplicities. And so we clearly get an equation among the intersection multiplicities. And this equation does also hold without this assumption. So even if FG do have a common component, so we don't have to put this there. So in any case, we have that the intersection multiplicity of F with G times H is intersection multiplicity Fg plus intersection multiplicity of Fh. And in the case where we can apply A, this just follows from that using that construction. In the other case, we'll just see why it does. It's actually quite simple, basically, because both sides say infinity. You already know. Yeah, so let's say something about the proof. And so the thing about these exact sequences, so if you had them already in commutative algebra now, is that they are an incredibly useful tool. But to show that something is an exact sequence requires a lot of checking. Because, I mean, you'd first of all have to check that these maps are even well defined that I claim to exist. I mean, after all, they start in quotient spaces. So we need to check those two are well defined, and then we have to check these three conditions, which in that case often are just two inclusions. You would show like the image of that is contained in the kernel of that and vice versa. So there's a lot of things to check, and most of them would just be standard checking with really nothing happening, so sort of obvious stuff. And you usually don't want to write down everything because it's just tedious checking. And so I actually want to restrict here for writing down and these to one thing only, which is the most interesting part of that. And let's say something about the proof. So for A, so among all these things, so let me say, so let's put check here, the following, which I don't want to do here, is that these maps are well defined. That is sort of, let me just say something about this and not write anything down. That is sort of clear, right? So if you start anything here, well-defined means if you start in the kernel, if you start in FH, you'll get 0 here, right? But if you multiply anything with G, you'll land in something that you mod out. So you'll be 0 here. So that's why the first thing is well-defined, right? And then if you go from here, if you're in something in here, if you have F or GH, then both of them are, so this is again F, this would be a multiple of G. So if you start with something that you mod out here, it's also modded out here. So that's why this is well defined, right? So both maps are clearly well defined. And what's also clear is like a projection like that is always surjective, right? I mean, you can take the same polynomials you had there and take its class in the starting space. So the last map, the projection, so what we call this pi is surjective. And what's in fact also clear is that the image of the first map is the kernel of the second. If you start here and you're in the image, if you take something and map it, have something in the image, which is G times something. If you have G times something and map it to here, you mod it out because G is down there, right? So the composition of the two things is clearly 0. And similarly, you could do it in the other way. So if you have something here, which will be in that, then it must be a linear combination of F and G. So something times F plus something times G. But F is modded out anyway, so you don't care about F. So essentially, you have something times G. But if it's something times G, then it obviously comes from that because I mean, these parts are all clear of that part. In particular, they would hold whether or not F or G have a common component. It really doesn't matter, right? So that's all simple. So that means the image of the first map, so of this times G map, is the kernel of the projection. In fact, the only part that is sort of interesting is the injectivity of the first map, and that might actually be false if they don't have a common component. If they do have a common component. So let me just put a check mark here. So the only interesting part is that this map times G is injective. And let me just check this one, and then the other, as I say, are quite simple. So why is that? So assume we have something in here, and then we multiply it with G, and it happens to lie in that. So this means we have some element. So assume we have some F over G, I guess I want to write it, in the first thing. That maps to 0, like in OP modulo FH, mapping to 0, i.e., so what does the map? It multiplies with G. So we have F over G times capital G. And that must be 0. Here means it's a linear combination of the capital F and capital FG. So that means we can write it as some other polynomials, F prime over G prime times F plus F double prime G double prime times the GH. Right? So that's exactly what it means. I always don't like these denominators, so I'll just multiply with them. And I can, of course, do that. I mean, I don't know anything about these f's and f primes, and so anyway, so multiplying with the denominator. Would, like a common denominator, so we can assume that we have this without the denominators, right? So that fg is this plus f prime gh, so after clearing denominators. But that means that now if we look at capital G, then capital G divides this and that, so also this. So this means that G must divide f prime f. But G and f are co-prime by assumption. So there we need this now. And that means G divides f prime. We need fg co-prime. So G divides f prime. So that means f prime is some G times something. We call this A maybe. And then we can cancel that one. Okay? So it means, let me just insert this, f times capital G is G times A. This is the f prime, and there's still f. And then we have plus f prime gh. And that's an equation in the polynomial ring, which is an integral domain, so we can divide by G and get f is a capital F plus f double prime h. And that means our f lies in the ideal of f and h. And so that means it's 0 here. And so f over g is as well. F is 0 in OP mod fh. And that's injectivity, right? If there's something that maps to 0, then it is 0. So again, this is just some checking, right? I mean, it's the most interesting part of the checking, but still it's just some computation. And that shows we have an exact sequence. And so let me just finish this off by saying here, so part B, of course, the statement B, as I said, just follows from the construction. If they don't have a common component, if f and g have no common component, then this follows from A by taking dimensions. And if they have a common component, then we know already by this homework that I cited that both sides are infinite anyway, right? Because if f and g have a common component, where's the equation that we want to show? Here. If f and g have a common component, then they have a common component as well, right? Because that has the same component as well as that. So it means there's infinity and here's infinity, and it's just true. Okay? So then both sides are infinity. And that shows it in any case. And so, as I said, we'll see that these properties are actually sufficient to always compute this. I think now we know enough about this. We also can look at some geometric interpretations. We all do this next week, and a little bit already on the homework. The time is up, I think. If there's any more questions. Otherwise, then we'll just meet either next week or the week after or in the video. Whatever, right? Okay, that's it for today.